Okay, in our last lesson, we learned about how to find the position between any two locations on a normal curve. So before that, we had learned that the normal curve is special. If you take one step up and one step down, you got 68%. Two steps up and two down, you got 95, etc. And then we found out, well, what happens if you're not on a particular step? What we found was that you could do this anyway between any two locations. What's really going on behind the scenes is z-scores and calculus. Um, but our calculator will do all the magic for us. So today we got a super important idea, and it begins with this. If you can't read that, bad handwriting. That says population distribution. And what I want to do is have you imagine that we are looking for the mean in the center of a normal curve, but we're not exactly sure what it is. So what would happen is that you have a bunch, this isn't quite true, this is a continuous distribution, but I want you to imagine that we were looking for the average height of students at the University of Findlay. Or let's change it, the average score on an admissions test to the University of Findlay. So that should be a normal curve. And all the people at the University of Findlay make up this distribution. Everybody's in here. So there's some average for this entrance exam. And some people scored very close to the average, and some people might have been well above it, and some below. So every dot here represents a person. Well, what if I didn't know that mean? So I'm not sure what exactly it is. If I just randomly came up to a single student and I said, hey, what'd you get on that test? They tell me, and I say, okay, we're just going to assume that your score would be a pretty good guess for what the mean must be. If you think about that for a minute, it doesn't make any sense because there are such a variety here. You might be getting a person who did very poorly. You might be getting a person who did extremely well. And so just taking a random person and hoping that their score is a good representation of the mean, that isn't going to work very well. But what if we tried a different idea? Suppose that I took the score of everybody in our classroom, averaged those together, and took a look at the number that I got. So what I'm saying is, what if I worked with the average of everyone in Stats 123, Math 123? Wouldn't you agree that that is most likely going to be a better guess at what that center number would be, what that average should be? So what I'm saying is I'm working with averages instead. So I think you can kind of see inherently that would be a better way to guess at what that missing mean was than the way we were doing it before. Now, suppose that I went to the class next door and I did the same thing. I took their average of all of their tests and used that to try to guess the mean. Couldn't you see that that's going to probably be different? It's very unlikely that if I took 30 students out of the classroom right next to ours, averaged their score, that it would be the same as ours. I mean, it could be close, but it's not going to be identical. And suppose I went all through all the buildings, all the classes that were being held at this exact moment, and I kept taking samples of all the people in the room. Well, what would happen is I'm starting to build something called a sampling distribution. Now, the dots in this distribution are not single people. They were up here. This was everyone who took the entrance exam at Findlay. But these are averages. They're X bars. There I took everybody's score, added them up, divided by the number of people. Okay? So this is called a sampling distribution. And this is full of much better guesses at the center than this one would have been. Okay, now, yeah, let's say this next. And can you see that the center of this sampling distribution, there is no reason why it wouldn't be the exact same center as this one up here. So if you knew, remember my math language, what we said about this population distribution, that means it's normal. And we've got the mean and the standard deviation. Well, why would the center of this curve, where I'm using all the same people that I did in the population curve, I'm just averaging them together, why would the true middle of this be any different than the true middle of all the individuals? It's made up of the same people. It should be the same center. And so what we're finding here is that this sampling distribution is also normal, and it has the exact same center. And that's the power of this trick. we could work down here in this sampling distribution to try to find that missing number, because these dots, these groups of people, give good guesses at the middle. So you following that? So what we're saying is we had this population curve, but suppose we didn't know the middle. Up here, any individual score is not a very good guess at what the middle would be. But if we move down here and we use groups of people, each of these dots should be a pretty good guess at the middle. It's a much better. Now, if you're following what I'm saying, let's suppose instead of asking groups of 30, classrooms of 30, we went around and we found classrooms that had 100 students in it. Wouldn't you think that if I averaged their scores on the entrance exam, that would make an even better guess at the middle, at the mean? So every dot, if it became dots full of 100 students being averaged, it should be even better. And if I went to 200 students, what we would find, my picture may not do it justice, but what we would find is the bigger the group of people you use to make your average, the better every dot is going to be at guessing the middle. In other words, your curve is going to get tighter and tighter, which is a fancy way of saying your spread is going to get narrower. So here's what I'm saying, if you're not tracking with this. In the sampling curve, the standard deviation gets smaller when you work with these group of people. And in fact, it gets smaller by this. Take the standard deviation of the population curve and divide it by the square root of the number of people in your group. And so if you think anytime you're dividing by a number, you're making this standard deviation smaller. So here's what I'm saying in a nutshell. This population distribution has a mean and a standard deviation, but if you work with samples, groups of people, you have the very same middle, which is a very helpful thing that's going to be very important to us the rest of the semester. And the larger the group, the smaller the spread. It gets tighter and tighter because every guess, every group of people would be a better guess. They would all be in likelihood closer to the middle. So if you use a bigger n, this becomes a smaller number. All right, super important idea, population distribution and sampling distribution. Now, before we look at what the problems are going to look like here, let me tell you here. A fancy name for this is called the standard error of mean, in case you see that in the book. If you divide that standard deviation by the square root of n, it's called the standard error. Okay, so that's the really important idea, but there's one more piece to it. Suppose that we were at a school, we were trying to find the average height, but we were at a school that excels at basketball. Suppose we were a basketball academy or something like that. Do you see that in all likelihood, if we were a basketball academy, we would have a great number of students who were taller? So basketball players tend to be. So we're looking for the mean. But our population distribution of all the individual people at our basketball school, it is not a normal curve. It is skewed to the right because we have so many tall people. So because of that, all of our tricks, the empirical rule, all of that madness that we've learned before would be completely worthless. It only works on the normal curve. Well, a very interesting thing happens with something called the central limit theorem. And it says that this trick that we did from moving from the population to the sampling distribution, it is so good that if you move to a sample distribution, even though the population wasn't normal, if you start working with averages, this crazy thing happens. It just has to do with the principle of working with averages because you're randomly selecting people from underneath this population. You're randomly selecting dots. Well, if you randomly select things, it begins to take on the shape of a normal curve. So just by how averages work, if you start to sample large enough, it will turn the sampling curve into a normal curve. And what is large enough? If n is greater than or equal to 30 is generally the number that's accepted. You can have a population where I can't do anything with this. I can't do any betweens. I can't do normal CDF. But my sampling curve, I can. it has turned a population that wasn't a normal curve into a sampling distribution where I can do the tricks. What's the value of this? I could try to find the mean for this population down here in this sampling curve, and it would work. Okay, so here's my last point here. If I can find it. Okay, let's look at a problem. So a distribution has a mean of 90 and a standard deviation of 15. The only thing that's changed is now we're going to move to a sampling curve, and we're drawing 25 people at a time. What's the probability the sample mean is between 85 and 92? This is exactly the same thing we were doing before. The only difference is we're going to work in the sampling curve, where the mean stays the same and the standard deviation gets divided by the square root of the sample size. You're going to do a normal CDF here from 85 to 92. This is the region you want, but your curve is now a sampling curve, and you're not going to use the mean of 90 and the standard deviation of 15. You're going to use a mean of 90, and you're going to use a standard deviation, which happens to be 15 divided by the square root of 5, so that would be 3. Just crunch this. So now the sampling distribution has this as its mean and standard deviation. Because samples are better, it tightens the curve. That's all I'm saying. And so you would do normal CDF, 85, 92, and then, well, lower, and here's your upper, here's your mean, there's your standard deviation. Okay? All right. I don't even think there's anything else I need to say about that. I think that's it. You do exactly the same thing we did before. And if you were trying to do the inverse norm, you just have to work with the new standard deviation that you get in a sampling distribution. All right, my final point here, and then I will leave it alone. If they tell you the population distribution was normal, then you know that the sampling distribution is going to be normal. That is always true. But if they tell you the population distribution is not normal, then the only way you can do this normal CDF trick down in the sample distribution is if n was greater than or equal to 30. That's our trick to turn a skewed distribution into a normal curve. Okay, I think that's all you need. If you have any questions, let me know.